We're good. Yeah, so the question somebody just asked was, is the scope of this for gas turbines and nothing else? No, so certainly the examples I gave in the beginning were gas turbines. The scope of this is, I would say, pretty much for any flowing device, as opposed to a constant volume engine type application. So a boiler, a water heater, gas turbine, any kind of burner. Did I answer the question? We're good? Okay, great. Thank you. I think so. Am I good? Okay.
All right, thank you.
All right. Okay, does anyone else have any questions? Okay, well, let's start back up. So just a quick refresher. Remember, so I've been talking about some of these intrinsically transient or unsteady issues around steady flowing devices. And so if you remember, the approach I took was the first hour yesterday, I just talked about applications and interesting real-world problems. And this is one of the slides I showed you where we talked about blowout, and I gave you an example from an aircraft engine and for power generation. But what the focus of what we started on talking about then yesterday was, in order to understand the conditions under which a flame can and cannot stabilize, we need to sort of add to our toolbox understanding of two important phenomena. One is what happens when flames are in regions of very high shear. And that's what we're going to talk about for the next hour or so, is flame stretch. And then the other thing I want to talk about is, when you talk about flame stabilization, you're talking about a flame that has a beginning point, it has an edge. So I want to talk about edge flames. So those are the two main things that we're going to be getting through today. We'll see how far we get. But so yesterday I kind of motivated the discussion. We talked about what happens when a flame isn't flat, and what happens if the flow field isn't one-dimensional. Now, just a quick clarifying question. Somebody came and asked me yesterday. They said, "Well, hold on. You told us that when a flame is curved, the stream tubes aren't straight anymore," and you're absolutely right. So I was just trying to demonstrate in this example that the issue is that the streamline and the diffusive flux vector aren't aligned. All right. So I'm not trying to draw a real flame. So this, you can think of this as an isothermal flame. Any flame with a real temperature jump would distort the approach flow stream tubes, and they wouldn't be straight lines. But again, the key factor the common theme to both of these two problems was that you had misaligned convective and diffusive fluxes. And we're going to talk about flame stretch with a slightly different approach today. But again, remember what I had said yesterday, that for steady state problems, now when there's unsteadiness, something slightly different happens. But for steady state problems, flame stretch, the reason that it has an influence on the flame fundamentally derives from this misalignment of the convective and diffusive fluxes. And what that does is it changes the energy balance in the preheat zone. That if you just take a flat laminar 1D flame with, and you kind of take a one-step kinetics viewpoint just to get things started, if you write an energy equation for the preheat zone, you have this balance between convection and diffusion, right? There's this net convective flux of enthalpy across the preheat zone, and that's exactly balanced by diffusive flux backwards. And so the two balance. Once convective and diffusive fluxes misalign, then that enthalpy balance is potentially broken, and you have a situation where you can either add enthalpy to your preheat zone or you can take it away. And then therefore you can have situations where your local flame temperature is higher than the adiabatic flame temperature or lower than the adiabatic flame temperature. You can also have situations due to differential diffusion, which we talked about yesterday, where the local fuel-air ratio or the local fuel composition or the local reactant composition is different from the global average due to differential diffusion effects. Okay, so that's just a very quick summary of what we finished up with yesterday. Anyone want to ask a question or clarification on that? So we're going to dive into this a little bit more detail today. So if you remember, we had walked through, talked about Lewis number effects, we had talked about differential diffusion effects, showed how both of those, when you have curved flames or you have non-one-dimensional flows, can alter this energy balance. And we had done worked through an example for the Bunsen flame tip specifically, and we looked at a fuel where differential diffusion effect, where the fuel was more diffusive than the air, and we looked at a situation where the fuel was less diffusive than the air, that's methane and propane, and showed how you could have flames that were lower than adiabatic flame temperatures or higher for the methane case, and that those tendencies are flipped for the propane air case. Okay, and now, in this stuff, we're primarily going to talk about laminar flames here, but I want to emphasize, the same thing happens when you have a highly turbulent flame, because at least if you have a flamelit structure locally, what does turbulence do? Locally, turbulence curves the flame, which if you have a stretch-sensitive flame, changes what happens locally. And also, because of the velocity gradients, you have eddies with a given length scale, which means you have velocity gradients over a given length scale. Those also induce hydrodynamic stretch on the flame, and they change the local burning velocity. So when you have a stretch-sensitive flame, the burning rate can vary significantly along the flame. In fact, we've done quite a bit of work. There's quite a bit of work going on this very topic right now for turbulent flames, and we know that stretch effects can have very significant impacts on how fast turbulent flames burn. You take a fuel that's not stretch sensitive, you can take a fuel that is stretch sensitive, they can have identical laminar flame speeds. You put them in the same turbulent burner, the turbulent flame speeds can differ by a factor of 2 or 3 or 4 due to these stretch effects. And just to illustrate this, these are some nice DNS results of some different flames: propane, methane, hydrogen. And particularly the hydrogen, which is very diffusive, and there's really, really strong differential diffusion effects. You can really see the difference in, well, these aren't really reaction rates; these are mole fractions of OH. But the positively curved leading edge of these hydrogen flames, really, really fast chemistry. These trailing edges, which are negatively curved or negatively stretched, the flame can actually locally extinguish in those cases. Yes, sir. Yes. How are they running at 0.27 for methane? I don't know what the temperature and pressure for this calculation is. I can't remember. All I know is that for methane, when you're that lean, you're going to have a negative Markstein length, which will give you a certain kind of sensitivity to stretch. I'd have to go back and look at the paper to see what the other conditions were. Okay, so now that kind of talks about what's happening inside the flame structure. Now what I want to do is work out some results a little bit more formally, and now I'm not in order to do the things that we're going to do for the next half hour or so. We don't really have to think about the flame structure, so I'm just going to treat the flame in essence as a discontinuity. All right, and if you look at Foreman-Williams' book, 1975, he defines flame stretch as 1 over A dAdt, and so A is a Lagrangian element of flame surface area. So if you imagine you take the flame surface, which in the flame here is a discontinuity now, and you take a Lagrangian element and then you track how much it changes dt later, 1 over A dAdt is the definition of stretch. So what it does is it quantifies the degree of stretch imposed on a differential flame surface element. So what I want to emphasize here is stretch is intrinsically it's a quantity that's defined for a surface, as opposed to strain, fluid mechanics strain, which is a volumetric quantity. So those of you who've taken shear flow, you'll know about there's this thing called the stress tensor, which quantifies the deformation. You can have shearing, or you can have changes in you can have normal strain or shear strain on a fluid mechanic element. That's a volumetric quantity. It applies to a volume of fluid. Stretch is a surface quantity. Basically what it says is that if you could take a fictitious surface, stick it in the flow, what is the fluid mechanic non-uniformities doing to that surface? Is it increasing the area? So that would make kappa positive, or is it decreasing the flame surface area? Stretch has units of 1 over second, so it's an inverse time scale. All right. So now we'll kick into some math here, and I'm not going to work through the details. I'm just going to show you the results, and I'm just going to kind of talk about physically where they come from. But if you work out the math for a Lagrangian fluid element, 1 over a dAdt, you can write it in terms of local quantities of the velocity field and local flame quantities in this way. So let's take a look at this. It's basically, let me come back here, make sure I know what I'm going to say. Basically, we can write it as a sum of two contributions. So what I'm going to call dut1 by dt1. So the subscript t here denotes the tangential direction, right? So for a surface, a given two-dimensional surface, we can define a local orthogonal coordinate system. So this script t1 would denote that would be the vector that's tangential to the surface. T2 would be the vector that's tangential to the surface but orthogonal to T1. And then N would denote the third orthogonal vector, which is normal to your surface. Okay? And so what this quantity right here, I'm going to call this the sum of these two quantities. I'll call it kappa A, which is right here. What this describes is the variation of the tangential flow velocity in the tangential direction. All right? So this quantity right here, you can see it's a little bit like a divergence, but not quite. It's not. It's really a stretching thing, and it's actually quite intuitive. It's sometimes given this vector notation, grad subscript t dot ut. All right. So in other words, what this quantity is, which I'm calling kappa A or hydrodynamic stretch, what we're saying is, if you take the flow velocity and you decompose the flow velocity into the components which are tangential to your flame surface. All right. So let's just think of, well, actually, let's go to this picture right here. So rather than thinking about a two-dimensional surface, let's assume we have a one-dimensional surface. So here's my velocity vector. Let me draw a picture here. So if the velocity vector, let's just say, look, these are local velocity vectors. So what I'm trying to draw here is that's this flow which is diverging through the flame. So if here's my surface, and this doesn't have to be a flame. I mean, stretch is defined for any surface. But so here I have this surface, and if let's say these are my instantaneous velocity vectors, I can decompose the velocity vector into a normal and a tangential component. And what I'm asking myself is this tangential component changing in this direction? Because I hope you can see this physically, that if this tangential velocity is the same along this whole tangential direction, there will be bulk translation of this surface, but there's not going to be stretching of this surface, right? But if this tangential velocity is changing in the tangential direction, the surface is going to be intrinsically getting stretched. Everybody with me? So it's not the tangential velocity that matters. It's the gradient of the tangential velocity in the direction tangential to the surface that you're looking at. That's what flame stretch is. Now, if you want to treat the flow upstream of the flame as incompressible, then you can also use the continuity equation, and you can say, well, the sum of this term plus this term will just equal negative dun by dn. So another way to think of it is the time rate of change of the normal velocity, the derivative of the normal velocity in the normal direction through the continuity, assuming you have continuity, assuming you have an incompressible flow upstream of this isosurface. But more fundamentally, what stretch is it's this variation of the tangential velocity in this tangential direction. That's what's stretching this interface out. Okay, so both of those examples that I showed you before were examples of hydrodynamic stretch. In both cases, you had a situation where the tangential velocity was varying in the tangential direction. I think probably it's a little it's reasonably intuitive why this example would be stretched through hydrodynamic means, because here you have a tangential velocity component in that direction. Here you have a tangential velocity component in that direction. You can see that this surface is going to be stretched. Its area will be increased. That's positive stretch. That's why this is a positively stretched flame. Well, let's look at this curved flame. This is a little bit trickier off the top of your head to see why, but we'll collapse, like I said, we can collapse it to a surface, the flame, and let's just think about why this front is negatively stretched. So what we need to do now is here the flow I'm assuming is just rectilinear. It's not changing in direction, just to make things simple. But again, what we got to do is we have to take the velocity and decompose it into a normal and tangential component, right? So we say, all right, I got a component that direction, and I got a component that direction. Same here, component that direction and a component that direction. So now if we take the tangential velocity, can you see why this is negatively stretched? Because it's compressing this surface. That the tangential velocity is changing in the tangential direction, hence this flame is negatively stretched. The tip of a Bunsen flame is negatively stretched. The leading edge of a turbulent flame is positively stretched for the opposite reason, right? So if I flip that flame around, and if these are reactants and these are products, and I draw my lines again, you can decompose it, and you can see that these will be pulling the flame apart. That's positive stretch. Okay, so that's the first term, hydrodynamic stretch, variation of tangential flow velocity in the tangential direction. So I hope, I have the math there, but I hope that you can kind of see it in your head. And if you want to figure out for yourself whether a flame is positively, negatively stretched, just remember that all you got to do is take the flow take the velocity vector, decompose it into tangential and normal direction, and ask yourself, what's the tangential velocity doing along this surface? Okay, now there's another part which I haven't really talked about before. This is an intrinsically unsteady piece, and this happens whenever you have a non-stationary flame that's curved. Okay, so this part right here is Vf dot n times del dot n. Now del dot n, if any of you remember your vector calculus, n is the normal vector. The divergence of the normal vector is 1 over the radius of curvature. That's right here. Well, for a cylinder, it's 2 over the radius of curvature for a sphere. All right, so this term is related to curvature. Vf here denotes the velocity of this surface. All right, again, it doesn't even have to be a flame. It's a surface by our definition of stretch. So what this tells you is if that you have a curved surface and there is a velocity, and that surface is moving in the direction normal to itself, that flame will be positively stretched. All right, and I think you can probably see why, at least for a flame, is because if it's curved, well, here, let's just do it. Here's my curved surface. This has a non-zero divergence vector for the normal velocity. And if this surface has a non-zero Vf dot n, right? So that means that this is moving out. Well, what's going to happen to the surface area? It's going to grow, right? So some instant later, that surface area will grow. Okay? So just want to emphasize here, so this curvature effect is an intrinsically unsteady effect. I just drew for you a curved flame there. And there, the reason that flame was stretched, it wasn't so much the curvature, it was the fact that there was this tangential velocity with respect to the flame that caused the previous picture that I just erased to be hydrodynamically stretched. Does anyone have a question about that? Yes? So in a real flame, you have hydrodynamic stretch effects, you have unsteady curvature effects, and the overall stretch is the sum of them in an unsteady flow. In a steady flow, where the flame is just sitting still, all the stretch comes from that term right there, the hydrodynamic term. Okay. So, we already talked about stationary flames, so I'll just stop there. Now, you can write this expression for flame stretch in an alternative way, all right, for a flame. And now for a flame, what you can do is you can say, you know what? I can relate the instantaneous velocity of the front to the local burning velocity and the local flow velocity. Okay, in other words, let me just explain that real quick. So if this is my flame, it's going to be propagating at the flame speed. And remember, the superscript U denotes the flame speed with respect to the reactants, the unburned, right? That's what that superscript U means. So if these are reactants, these are products. You can't see over there, can you? There's a seat right here, which might be a little bit more productive for you. I'm sorry. Can you see? Okay. I'm trying. You just keep reminding me. Don't be embarrassed to raise your hand and tell me to write that I got to work on the parallax. But okay, so if these are reactants and these are products, the flame, a premix flame, is propagating normal to itself, right? So the flame is moving at this, with respect to the reactants, it's moving at a speed of SU. And so this velocity vector would be in the direction SU dot n. And then, you're going to have then the flow itself. If this was a passive, if the front were purely a passive scalar that didn't propagate, this front would still move just due to the flow velocity, right? So if I have some flow velocity vector U, so U plus SU n would be the net velocity of the front, and that equals, oops, I'm going off the board here. Well, I'm just writing this formula. So VF would equal that, which is the formula that I have here. So we can relate the velocity of the front to the flame speed and the flow speed. So important to remember, VF is not the flame speed, it's not the flow speed, it's the speed of the front, which is not equal to either. The flame propagates normal to itself. So anyway, if you substitute this expression for VF into, this equation here, and you do a little bit of juggling, which I'm not going to go through the details of, you can derive this alternate expression for flame stretch. All right, and you can write it as two contributions, kappa S, and what I've called kappa S and kappa curvature. The reason this is called kappa curvature is, again, you see that del dot in term, which is, so this is basically burning velocity divided by radius of curvature. This term right here is it's a flow non-uniformity term. You can see that you have to have gradients in the flow velocity, that the velocity has to have spatial gradients for this term to be non-zero. And another way you can actually think about this term, this first term, is it's equal to the, it's actually, you can directly relate it to the fluid mechanics strain. So if I'm going to call S, if S is the rate of strain tensor for the flow, so it's, dUI by dx, in tensor notation, S would be, Sij would equal 1/2 dUI by dxj plus duj by dxi. But the reason I like this particular expression as an alternative, I think this previous one is more physically clear. It tells you what's happening. This one I like because what it does is it explicitly shows you the relationship between fluid mechanics straining and flame stretching. All right? And one thing it does tell you is they're related, but they're not the same, right? You could have a flow where, even where S is 0, even where there's no fluid mechanics straining, you can still have a stretched flame, right? Because you have these two terms which survive. So fluid mechanics strain, flame stretch, they're not the same. Now, this is just purely Tim Lieuwen's private notation. Oftentimes people talk about flame strain. And there's a lot of books that use the word flame strain. I personally don't like to use that word because I like to reserve the word strain for this volumetric deformation of the fluid elements, and stretch, which has more of a surface feel to me. I like to say flame stretch, flow strain. But if you look in the literature, you'll hear people talk about flame strain, and they're talking about what I'm calling flame stretch. It's this kappa quantity. But that's just a small aside. Okay, so we're actually going to dig into this a little bit later when we're going to dive into flame stabilized in shear layers, and we're going to actually develop an expression for the stretch rate of a flame in a shear layer. And I'm going to come up with an explicit relationship between flow strain and flame stretch, and you'll see that they can differ by orders of magnitude in some cases. Yeah. So the front speed is the speed with which this surface is moving with respect to your observer. It's not the flame speed is the burning velocity. The burning velocity S, or what I'm calling S superscript U, that is the speed of the front with respect to the reactants. So for example, well, I'll tell you what, let me just give you a nice little example here. So if I have a flame, let's suppose I have a flame speed of 10 centimeters per second. Okay? Front. So this flame is moving at 10 centimeters per second with respect to the reactants, right? Well, okay. Let's suppose the flow here is moving 40 centimeters per second. What's going to happen? This flame will be consuming reactants, but the whole front is going to be moving backwards at 30 centimeters per second. So VF, and this example is 30 centimeters per second. SU, or negative 30 centimeters per second, is 10 centimeters per second. And U would be, I guess, negative 40 centimeters per second in this example. Okay? It's the speed of the front with respect to the reactants. Or if it's S superscript B, it's the speed of the front with respect to the products. And if you want to actually say, well, in reality, I'm going to add a complexity because we're going to dig into this a little bit later. In reality, flames aren't infinitely thin, and so you can define an infinite number of flame speeds, and really what this is it's the speed of some iso surface with respect to the local velocity. So you can imagine a real flame has thickness, so you can define a bunch of iso scalars. They could be iso concentration vectors or iso temperature vectors. And so S superscript U is kind of you're taking the iso surface right at the leading edge of this front, which is the S superscript B would be on the back, but you could define it anywhere else as well. And we're going to get into this when we start talking about really, really stretched flames as things start to get a little bit ambiguous because the gradients start to become on the order of the flame thickness. Anyone else have a question? Okay. So I talked about unsteady effects, but let me just bring this motion of curved flames back. And I mentioned this yesterday, but I want to emphasize again that a stationary curved flame where the streamlines are normal to the front at every point is an unstretched flame. Right? So it's not curvature itself that stretches it. It's the misalignment of streamlines with your surface normal. Or curvature in motion gives you stretch. Right? So for example, if you have, the example that I drew up for you yesterday when we were finishing was if you could somehow have a point source of reactants, and so your streamlines are going out like that, and then your flame sits like this. If these velocity vectors are everywhere normal to the flame, and the flame is stationary, this is an unstretched flame, right? Because the hydrodynamic stretch is 0 because there's no tangential velocity component. You have to have a velocity component tangential to the front to have hydrodynamic stretch. And the only way then this curved flame would be stretched is if it's changing in time through this second term right here. Okay. Now I'm going to now talk about starting to quantify the effect of, so we've talked about what stretch is. We phenomenologically talked about why it would impact the flame's burning velocity. Now I want to start being a little bit more quantitative in terms of the flame's sensitivity to stretch. And so basically, just to summarize, if you have some burning velocity, and specifically I'll talk about the flame speed with respect to the reactants, S superscript U. I'll just tell you, I hope that I've convinced you now that it's a function of the stretch rate. All right? Now, kappa. So SU is a function of kappa. Now, it also turns out, I'm not going to prove it to you, but I've shown you that there's different ways you can stretch a flame. You can have, let's back up here. You can have what I call kappa A, which is hydrodynamic stretch. You can have this term I call kappa B, which is unsteady curvature-induced stretch. Or, we rewrote it where we explicitly decomposed it into, over here, this curvature term here and this term that I called kappa S. So there's these different components of stretch, but it turns out that in the weak stretch limit, the flame doesn't differentiate between these different methods of stretching it. All it cares about what's the total stretch, kappa. That's not true for large stretch in the nonlinear case, but for weak stretch, things like the flame speed, things like the flame thickness, they don't care. And so what we can do here then is, so that's kind of the first result, is that we don't need to worry about these different mechanisms for stretch. We can just say we have an overall stretch rate. That's all the flame sees. Now for weak stretch, what we can do is we can expand this thing in a Taylor series, right? So we can say that this will equal S superscript U when there's no stretch, when kappa is equal to 0, plus kappa times ds superscript U times kappa. At kappa equals 0, plus kappa squared over 2 d squared s superscript U by et cetera, right? And so for weak stretch, what we can do is we can just hang on to the first term in the Taylor series. We can eliminate that term right there. And what we can then write is, and actually the formulas are already on your page, I'm just rewriting them for myself. This term right here, we'll give it a superscript naught. And remember, I explained this notation to you yesterday. The superscript naught here denotes the unstretched value. So this is equal to the unstretched value plus, or for historical reasons, it's given a minus, what's called the Markstein length times kappa. All right. So this Markstein length, and I'm going to give it a superscript U here to denote it's the Markstein length defined with respect to the reactance. I could just as well write this as, if I wanted to write, this is the flame speed with respect to the reactance, I could just as well write it with respect to the products, S superscript B. I could do the same thing, and you could define a Markstein length with respect to the products or any other isosurface through the flame. So that's where this thing comes from. You start to get a lot of subscripts. But anyway, so now what this is called the Markstein length, okay, which we introduced yesterday. The Markstein length is purely it's a dimensional quantity. The reason it's called a length is it has units of length. It's basically a dimensional sensitivity of the flame to stretch, right? So even if you have a stretched flame, kappa can be non-zero, the flame speed could still equal its unstretched value if the Markstein length is 0. So an example of that could occur if you have a Lewis number 1 flame with no differential diffusion. You'd have a flame that's stretch insensitive. So although it's stretched, the burning velocity, the local flame temperature doesn't care. Now, as I mentioned, you could also write the definition of the Markstein length. It's not unique, and it's a function of the isosurface used to define it. So, for example, if we wanted to define a flame speed measured in a reference frame with respect to the products, you could do the same thing and write S superscript B as SB naught minus delta M times B over kappa times kappa. Same thing. And the Markstein length defined with respect to the products and the reactants is not the same thing. Okay, so this is a dimensional expression. All right. Now we can non-dimensionalize it by just dividing everything through by SU naught. So we can say SU, excuse me, over SU naught is equal to 1 minus let's see here. Make sure I use the same notation as your notes. And basically, I'm just going to multiply and divide by the unstretched flame thickness here. And I'm going to do that so I can get non-dimensional quantities. Can you guys see this in the back down here? This room is not well set up to see the blackboard and with the thing on. I apologize. Oh yeah, there you go. Look at that. The other thing I was going to say was if we could drop another screen, use that screen. But yeah, let's just use the whiteboard. Good idea. Yeah, I don't have a steady hand. Let's just flip this around. Oh, bummer. Not going to happen. Going to have to be a little bit more tricky. Oh, careful, careful. Wall, wall, wall. There we go. Sorry about that paint job. Thank you. Okay. Anyway, so, well, but what you can do now is we're going to call this ratio the Markstein length normalized by the unstretched flame thickness. We'll call that the Markstein number. So that's now we have a dimensionless number. Okay, and I'm going to call that MA. And I apologize, this notation gets a little bit confusing, but I'm just trying to be very rigorous. MA, I'm going to give it a superscript U to denote that it's the Markstein number defined with respect to the reactants. And this quantity here, remember kappa has units of 1/2. So it's a straining time scale, right? Now notice that the ratio of the flame thickness, the flame thickness over the flame speed, that's basically a chemical time scale. And so what we have over here is a ratio of a chemical time scale to a flow straining time scale, and we're going to call that the Karlovitz number. Okay, Ka. So when put everything together, what you end up with then is the dimensionless sensitivity of the flame to stretch is 1 minus the dimensionless stretch rate times the dimensionless sensitivity of the flame to stretch. Okay? So now, we've talked about a lot of physics here before. We walked through examples with Lewis numbers less than 1 or greater than 1. We talked about fuels that were lighter than air or than heavier than air. That was differential diffusion effects. We talked about fuel-air ratio, how these sensitivities would flip from the lean to the rich side. All that stuff is buried in the Markstein number. Okay, so all those sensitivities are buried in the Markstein number. The Markstein number is a function of Lewis number, diffusivities, equivalence ratio, et cetera, et cetera. And so you can basically now take some of the ideas that we talked about before. So for example, let's just do this here. If we go back to this data, let's say this methane air data. We know for this flame that we're looking at a Bunsen tip, so we know this is a negatively stretched quantity, a negatively stretched flame. So we know that this cap is negative, or alternatively, the Karlovitz number is negative. And this is a situation where the flame temperature is sub-adiabatic, and I can tell you that the flame speed, well, you all know enough to know that the flame speed is then going to be lower than its stretched value. And so what that tells you then is that this, yes? Yeah. So the stretch rate is negative, and so when we normalize it, the Karlovitz number would be negative. But I mean, remember that the question was what's a negative Karlovitz number? I'm struggling with that concept. That's what you're saying, right? So it's just the definition is that, I mean, oftentimes we define Karlovitz numbers as positive numbers where we're used to thinking about the quantitative value of it, defining how quasi-steady the flame is. Here, the negative would just mean that it's negatively stretched as opposed to positively stretched. Yep. Anyway, so what this tells you then, like, for example, if you have a lean mixture of a fuel that's lighter than air, such as methane or hydrogen, or if you have a rich mixture of a fuel heavier than air, that would be a fuel with a negative Markstein number. You can just kind of work through all the analysis that we kind of worked through intuitively. That's a negative Markstein length. Alternatively, if you have a lean mixture of a heavy fuel, like propane, or if you have a rich mixture of a light fuel, like hydrogen, that would be a positive Markstein length fuel. So let's just go take a look at some data, and we can kind of illustrate some of these ideas. So this is a propane air flame. This is the reference that it's pulled from. These are, I believe this is data from a stagnation flame. So you can basically take, Chemkin or Canter or something, and you can stagnate two flows into each other, and you get that positively stretched flame. And so by changing the velocity of the jet exit, you can change the stretch rate that the flame sees. So it's a nice, convenient way to quantify stretch sensitivities. So anyway, we're quantifying the Karlovitz number here on the x-axis, and what you can see here is that your flame speeds are increasing with stretch when it's rich, and the flame speeds are decreasing with stretch when it's lean. Consistent with what we've talked about. So this is propane. Now for hydrogen, these effects can really be big. These Markstein numbers, these stretch sensitivities are really, really large. This slide right here is a little bit more quantitative. So basically the slope of this line is the Markstein number, right? Just following from the definition. This is the left-hand side. This is the Karlovitz number. The negative of the slope of this line would be the Markstein number. Here I have just purely the Markstein number here for a bunch of different fuels. And so what you can see is, for example, for methane, the Markstein number is negative when you are lean, in this case below about 0.75. It's positive when you are more on the rich side. And then you can see these heavier fuels, the slopes of these lines are in the opposite direction. Notice that this is now, again, Markstein number on the y-axis. So a value of 0 above is positive, below is negative. The other thing you can see about this is that these Markstein number values don't exactly flip at p equals 1, right? When we walk through that analysis, there's really a lot going on. There's, Lewis number effects, which it's hard to include Lewis number effects, differential diffusion effects. And in reality, all the arguments that I've been walking through are really one-step chemistry, so complex chemistry. But if you include all that stuff, the basic trends are right. You can just see that the flipping in sign from negative to positive doesn't occur at an equivalence ratio of 1. But in general, lean methane flames have negative Markstein numbers. Rich methane flames have positive. Lean and even slightly rich propane flames have positive Markstein numbers. Very rich propane flames have negative Markstein numbers. Let's look at pressure. How does pressure change the sensitivity of the flame to stretch? So here I have a bunch of, these are calculations now. These are flame speeds. And stretch rate is on the x-axis, so this is all dimensional quantities now. And here I have a calculation at 1 atmosphere, 5, 10, and 15. And don't worry about what's happening farther out here. These curves start doing some funny things. They flip around. They become nonlinear. These are strong stretch effects. We'll talk about strong stretch effects next once we finish the weak stretch stuff. But remember, the weak stretch calculation that we've shown basically predicts that these lines should be linear, that they should, at a kappa value of 0, they should intersect with the unstretched value, and then they should linearly increase or decrease at a slope proportional to your Markstein number. But what do you think is happening here? You don't have to answer this out loud, but notice that as you go from 1, as you increase pressure, what's happening to the dimensional stretch sensitivity of this flame? Well, it's decreasing. This would be a negative Markstein length fuel, right? Because the flame speed's increasing with positive stretch. And the way we've defined it, 1 minus, if this quantity is increasing and this is increasing, the only way that can happen is if this is negative. So this would be a negative Markstein length. But you can see the actual Markstein length, the physical Markstein length, is dropping as we go up in pressure. What do you think is happening? So in other words, the same stretch rate, at 1 atmosphere, the same, what would give you almost a factor of 2 increase in the burning velocity has much, much less effect on a 15 atmosphere flame. Well, all right. So the reason for this is that ultimately flames are stretch sensitive because they have finite thickness, right? So if you think about those pictures that we draw, let me just flip back. What's causing this diffusional transport across the boundaries of your preheat zone. Imagine I took this picture and I just collapsed the thickness of this flame. You can see that that effect would become less and less and less significant. It's a finite thickness effect that causes flames to be sensitive to stretch. So again, we have to differentiate between the stretch we apply to a flame and its sensitivity to that stretch. And so the flame's sensitivity to that stretch is very much controlled by its thickness. So when you go up in pressure, what happens? Flame gets thinner. So the same absolute level of stretch has less effect on the, less perturbation on the flame's internal structure. So this actually is one of these things which starts to make you a little bit worried about trying to understand things like blow-off when you, in a high-pressure application, when you do an experiment at 1 atmosphere, because the dimensional sensitivity to stretch scales almost linearly with pressure. So if you're trying to understand a phenomenon that's happening at 30 atmospheres, at 1 atmosphere, the flame's stretch sensitivity, which is going to control its whether or not it can stabilize, is a factor of 30 off, and you could be in a completely different physical regime. So now this is a dimensional plot. Now what I've done here is I've made my stretch dimensionless. So what I've done is I've normalized the stretch rate by the flame thickness and the burning velocity. So this is a Karlovitz number, and so what we're doing now is we're basically rescaling it by how thick the flame is. And now you can see that the dimensionless stretch sensitivity is not much influenced by pressure. So the Markstein number, at least for this case, for this hydrogen CO flame 3070, the Markstein number is pretty much pressure invariant. The Markstein length basically goes as 1 on P, 1 on pressure. Okay, anyone have a question? Yeah.
So, for example, like lowest number, you say it's easy to say that okay, ratio of heat diffusion is equal to. So for these kind of numbers, like the Karlovitz number and the Markstein, is there a more physical? I can kind of, if I move stuff around, I can see that okay, the Markstein length is the change in the burning velocity is supposed to change the stretch. But just for these
so, I mean, what these non-dimensional numbers try to do is they try to, well, what they do is they put, for example, the Markstein number as opposed to the Markstein length, it rescales the sensitivity by something that's physically meaningful to the flame. And again, what the flame sensitivity to stretch is directly a function of how thick the flame is relative to what's the length scale over which the blow strain happens. So whenever you non-dimensionalize something, you're just trying to take a physical quantity and rescale it by something that is physically relevant to the phenomenon of interest. Okay, so that's weak stretch. Okay, so remember the key step that we did here to look at that was we said the flame speed's a function of stretch. I'm going to expand it into Taylor series. I'm just going to keep the first order term. And so basically you just take a straight line from the unstretched value and the slope is proportional to the Markstein number or the Markstein length. Now I want to start talking about what happens when you have strong stretch, because flame extinction, if we want to understand flame stabilization, we know, I haven't told you this, but we know that what happens is when flames get sheared too much, they start to extinguish, and that's when flames let go. That's when they start to blow off. Now, all right, so there's a couple different concepts I'm going to throw at you here for strong stretch. The first one that I'm going to introduce is I'm going to differentiate between 2 burning velocities. And I introduced this to you before when I was trying to explain some nomenclature on some other slides. Now I'm going to define. Particularly, we needed to differentiate between a displacement speed and a consumption speed. All right? For an unstretched flame, they're the same thing, which is why you probably haven't worried about it before. We just, your combustion textbook says S sub L. But now to differentiate, I'm going to call S subscript D the displacement speed, S subscript C the consumption speed. So the displacement speed is the speed at which the flame is moving along its normal relative to the flow. All right? And it's, again, it's a function of whichever ISO contour through the flame that you want to pick. You can pick the front edge, and so then there would be the displacement speed with respect to the reactants, the backside, displacement speed with respect to the products, or you could pick anywhere in the middle. Now, as I just said, this value of the displacement speed is intrinsically a function of your reference surface. You get a different, I've differentiated yesterday and today between unburned and burned, but again, there's this continuum of values. Well, that's not such a big deal for weakly stretched flame because the approach flow is not changing that rapidly upstream of the flame with respect to the length scale over which the flame is happening. All right? But when you start to get critically stretched flames, flames which are close to extinction, what happens is that the velocity gradients which are causing stretch are on the same length scale as the flame thickness. And then displacement speeds start to become a very, very muddy business. In fact, they start to just it's not even a useful quantity anymore to look at. A simple example of why they're not is you can actually get negative flame speeds. And this always throws people off. How can a flame speed be negative? Well, and that's where the flame has a positive consumption speed. The flame is consuming reactants. But you can actually find a reference surface where the flow velocity is actually negative with respect to the front, and you can get negative displacement speeds. This is a simple example of this. Negative displacement speeds were first identified by Foreman-Williams, actually in this problem right here, where you take premixed flames and you stagnate them against products. And what he found was above a certain stretch rate, the flame popped across the stagnation line onto this side. And so the flame is propagating into the reactants, but notice the flow is basically going backwards through the flame. So the diffusive gradients are so strong that they're actually they're fighting the flow. And this would be a flame with a negative displacement speed. Any real flame in a high turbulent flame in a highly turbulent flow has lots of locations of negative displacement speed. I know I'm kind of twisting your brain right now. You're not used to thinking of negative displacement speeds, but this happens in real flows. Real flows have very, very strong velocity gradients. Real high turbulence intensity flows have very strong velocity gradients, and you actually get negative displacement speeds. Another good example of where this happens is at the leading edge of a turbulent flame brush. The leading edge of a turbulent flame brush is by definition positively curved like this. So you would have reactants and products. The flame is nominally consuming these reactants, but in fact the flow is going backwards through the flame. And generally these flames are known to have negative displacement speeds. So again, displacement speeds start to become not such useful things to think about for highly stretched flames because they just don't work. In particular, if you start adding unsteadiness to the flow, if the flow starts becoming time varying, the displacement speed becomes even more confusing and even less physically relevant. So that brings us to the consumption speed, which behaves. It's a much more well-behaved quantity. You'll have a much easier time with this. The consumption speed, rather than trying to define the velocity of an isosurface with respect to the flow, it's basically taking a consumption rate and suitably normalizing it to get a velocity. All right? So it's some sort of spatial integral of a chemical rate. So for example, you can define different consumption speeds depending on whether you're looking at the energy equation, or you can define a consumption speed for any species in your flow. Because what you can do is, for example, here's my energy equation right here. You integrate it along a streamline from basically all the way in the reactants to all the way in the products. Since you're integrating from all the way into the reactants into all the products, all these diffusive flux terms are zero because there's no gradients all the way in the reactants and products. And basically what you can end up with then is an equation like this, which would be the reactant density, rho superscript u, times the consumption speed with respect to the reactants equals the integral of the overall heat release divided by the difference in sensible enthalpy between the reactants and products. So again, don't get hung up on the math. The whole idea is you're converting a volumetric consumption rate into a velocity with a consumption speed. All right. And in the same way, you could take any species. So the subscript I here would denote the ith species. You could take the reaction rate of you could take the species equation, again, integrate it from minus infinity to plus infinity, and you could define a consumption speed for any given species. Now, you might be thinking, this just sounds really complicated. It doesn't make sense. what it comes to is that for highly stretched premixed flames, when we talk about flame speeds, a flame speed is intrinsically a reaction sheet type quantity. Real flames are volume. The heat release is distributed over volume. And, you know, we can kind of ignore that fact when flames are weakly stretched or when they're unstretched. We can say, you know what, to first order, I'm going to treat this flame as a discontinuity, and it's propagating at some velocity with respect to the front. When you really start to get strained, when the gradients start to become on the order of the flame thickness, that treating it as a sheet idea becomes more and more nebulous, and therefore treating it as trying to parameterize that sheet by a velocity becomes more and more nebulous, because it's a distribution. It's not a single sheet. Anyway, okay, so that's the consumption speed. Now, if we want to compare them, the unstretched consumption speed, so S sub C, superscript naught, so the superscript, again, naught denotes unstretched, and the displacement speed are the same. So we're not used to, whether you think about it in terms of velocities of an isosurface with respect to the reactants, or if you want to think about it in terms of converting a volumetric heat release rate or consumption rate into a speed, you get the same answer for the speed when it's not stretched. But as soon as the stretch rate becomes non-zero, you get a different value for these speeds. And just to illustrate this is a calculation. Again, a hydrogen CO flame for these conditions. And these are calculations. This is the displacement speed. This is the consumption speed defined with respect to the hydrogen species. This is the consumption speed defined with respect to the enthalpy. Anyone have a question? Okay, I think I'm almost done here. Not quite. Okay, so that's one effect of large finite stretch rates, is that we start having to think about these two different flame speeds, and we start having to kind of chip away at a foundation which you're probably all very comfortable with. You're all very comfortable with flame speeds. It makes intuitive sense. But in reality, it's a mental model. It's not quite physically what's really happening. And when you start to get strongly stretched, the problems with that simplification start to show up. The other piece of physics that I want to talk about here is the extinction stretch rate. And basically, if you stretch a flame, if you weakly stretch a flame, the burning velocity can go up or it can go down, depending on the Markstein number. Any flame, though, if you stretch it too much, it will extinguish. All right? And so I'm going to call this value kappa extinction. Kappa extinction is the maximum stretch rate that a flame can sustain before extinguishing. And so I've reproduced here this plot where I've plotted displacement speeds as a function of Karlovitz numbers. And you can see these curves, these are negative Markstein lengths. So the burning velocity increases with stretch. It increases. It keeps increasing. It starts to become nonlinear, starts to bend over. It hits a maximum. And then almost you try to stretch it just a teeny bit more. The curve starts to come down, but almost instantly it's all over. The flame extinguishes. So very, very small window between the peak and extinction. Now you might wonder what this is right here. This is an unstable branch, just like you have in kinetics with high activation energy. You get the S curve, and there's an unstable branch. We've just traced out that unstable branch to show that we've truly captured the extinction point. That's what this is right here. But bottom line is you have this extinction stretch rate. And so if we go back to this example that I showed earlier for pressure, if you look at this plot, I showed you that as you increase pressure, flames become less and less sensitive to stretch. What this plot also shows you is that as you increase pressure, flames can withstand much, much higher levels of stretch before they extinguish for the same reason. And again, this just tells you that if you want to study an extinction type phenomenon, related phenomenon like blow-off, like local flame extinction, in a high pressure application, you really have to think about what you're doing if you're taking data or if you're trying to simulate it or analyze it at lower pressures, just simply because there's just there's basically this 1-on-P scaling for extinction values. As you might expect, extinction stretch rates go up as chemistry gets faster, right? So as you go up in equivalence ratio, you might expect the extinction stretch rate to peak near stoichiometric values. So this is just a bunch of data. This is from Greg Jackson. For methane hydrogen air flames, this would be a methane-only flame, and this would be, with different blends. So if we look at a given plot, what you can see is that when you're on the lean side, as you head more towards closer to stoichiometric, you can withstand higher stretch levels before extinguishing. That makes sense. What this plot also shows you is that as you increase hydrogen fraction, the flame can withstand higher levels of stretch before extinguishing. And that is due to the fact that hydrogen is just such an exceptionally mobile species, and it has such a strong sensitivity to stretch, that adding just a little bit of hydrogen to your system can really go a long ways towards flame stabilization for this reason. Why don't we take a quick break? It's 3:03. Let's reconvene at 3:10.